Hey everyone, I am going to go over a problem that is one of maybe the most missed in organic chemistry when talking about conformers. So the question here is version, what conformer version of this molecule is the most stable? And to answer this question, you first have to think about what conformers are even possible for this molecule. So let's first convert this molecule into the conformers that could exist for it. Now, for every one of these molecules, these cyclohexane rings that have shown stereochemistry, meaning the wedges and dashes, there are two conformer versions of it. Remember that cyclohexanes can go through a ring flip. So there are two chair conformer versions. And I'm going to draw those two chairs by first just drawing the empty chairs. Excuse my poor line work there. Okay, so here are our two chair versions. You can see this is the chair flip in which you have kind of the left-hand side pointing up, and then on the bottom, the left hand pointing down, and vice versa. And we'll talk about what happens to substituents when they go through a ring flip. So to draw this cyclohexane as one of the conformers, I'm going to start by just drawing out a conformer that could exist and then flipping it. So I know that this group has to be up. This group also has to be up, and this group has to be down. I can't change that, or else I would change the stereochemistry of the molecule itself. But what can change and what will change between these is whether those exist in an axial or equatorial position. So starting with my isopropyl, I'm going to put my isopropyl this position starting here. So this would be carbon 1, 2, 3, 4, 5, and 6. And then this is going to be 1, 2, 3, 4, 5, and 6. Just so you see where I'm putting things. Okay, so my isopropyl on my first ring has to be up. And the position I've picked to start my drawing, this position on my chair, you can see that it is kind of pointed up. The actual ring is pointed up. And so I know that the up position here is axial. You can kind of use these points of the ring to tell you which way the axial is going. So I know that this axial is positioned up. That means that this axial has to be down. This axial has to be up. This has to be down, up, down. I'm just telling you where the axial positioning is on each of these carbons, and notice that it alternates. It helps if you pick one of these points that's very flagrantly pointed up or down as a starting point to think about where your other areas are also pointed. Because I always remember that, for example, here, the axial is up here and the equatorial is down here. And again, it's just going to alternate as you go around. And the same is true for the axial position of each carbon. So I know that the equatorial position here, there's nothing on it, but it is facing down. That means that the equatorial position here has to be up, down, up, down, up. Again, it alternates from carbon to carbon. That's going to help me determine that even though I know this position is up, and I'm starting here, it has to be in the axial positioning because on this carbon, the up is axial. So on point 3, you'll notice it's also up. And on this carbon, the axial is also up. So here's our CH3 group. Again, remember these alternate. So I know this axial is up, this axial is down, up, down, etc. Okay, so getting over to carbon number 5, here it is in a down position. So let's think about what our positionings are facing. Notice that this has a slightly upturned point. So that means its axial is up and its equatorial is down. So this is equatorial, the way that it's written. So right now, just as a reminder, this is axial and up. This is axial and up. And this is equatorial and down. Again, at this position, the way that the ring is drawn, I cannot have an axial facing down with my other positions as axial up, because that again has to alternate per carbon. Now, when you go through a ring flip, you will see that each of the up and down stays the same. So up still is up. I can't change that these are up and down because that would change the stereochemistry. Down still is down. But in a ring flip, my equatorial becomes axial and my axial becomes equatorial. And again, I could just figure that out by drawing it, and you'd see that these have to be that way, or you could just write out the opposites, equatorial, equatorial, and axial. But let's draw it out. So now notice that the same point, number 1, is facing down. That means that the axial position is down and the equatorial is up. And again, I know that my group is up, so it has to be equatorial up here. Notice again, flipped from our last ring. Position number 3, again, was an axial up. And after the ring flip, we see that this point's axial is facing down, but it needs to be an up group. So the equatorial is up here. Again, that means this is now an equatorial up. And lastly, position number 5 with our methyl that's facing down. If we go around, we see that this position is now kind of pointed down, meaning its axial is down. And we do indeed need a down. So this one is axial down. Like I said, you could have gone around and just flipped your axial to equatorial and figured out what the other ring would look like. So these are the 2 conformers that can exist. One in which the isopropyl group is axial up. One of the methyls is axial up, and the other methyl is equatorial down. The other version that can exist is the isopropyl as equatorial up, one of the methyls as equatorial up, and the last methyl as axial down. Now, for the rule of stability, we know that we want most of our groups, or the most groups, side chain groups that are carbon based, to be equatorial. Equatorial is the more stable position of the two. So the more groups that exist in an equatorial positioning of your conformers, the better. If you have to choose, if you ever have a choice between two different conformers where the same number of groups are equatorial, remember that bulkier groups, when in equatorial, will lessen the energy of the molecule overall. So in this case, we want to prioritize, for example, putting our isopropyl in an equatorial position. So conformer number 2 is going to be the conformer that is the most stable because, again, our isopropyl, our bulkier group, is in an equatorial position, but also it generally gives the most groups an equatorial positioning as well. Notice we have 2 groups, equatorial and 1 axial here. And that is how you would solve this problem of stability.